Okay, good morning everybody. My name is Nikunj Kela. I work for Qualcomm San Diego automotive sector, and today I'm gonna go over our approach to achieve platform resource abstraction using power and performance domain over SCMI. Agenda today, I'll go over the motivations, why we are doing this, then our approach, how we are achieving using SCMI the abstraction, then a high level architecture overview, the current status and the future plan. This slide shows the complexity of a peripheral device driver. A peripheral device may belong to a power domain, so there will be a power domain provider driver that it needs to interface with using PM framework. There may be a reset, it may perform certain resets, then it needs to interface with the reset control driver using reset framework. The peripheral device driver may also need to deal with bunch of clocks, and then this it needs to interface with the clock driver using clock framework, GPIO pin control driver, regulator provider driver. It may also have to it may have some PHYs, then it may need to interface with the PHY driver. Then PHY may in turn have its own resources like clocks, it may have its own power domain, so then their provider driver, PHY driver has to interface with. The peripheral device driver may also have to do some bandwidth voting, so it may have to interface with the interconnect driver using interconnect framework. So as you can see, a peripheral device driver really gets complicated, and we also need to implement so many platform resource driver. So what we are trying to solve here is we are trying to simplify things in the peripheral device driver by moving away all the complexity, and then also we are trying to improve upon on the our development cycles. We want to cut down the work that we need to do for resource drivers, so we can ship the product quickly in the market. This is a very high level introduction to SCMI. SCMI is an OS agnostic interface for system control management. It's split in two layers, protocol and transport. Protocol means the services that are being provided, for example clock, voltage, power domain and so on. Transport is the mechanism by which the two entities, one the agent who is the requester of the services, another the platform which is the implementer of the services, communicate, like mailbox, SMC, VertIO. And as shown in this picture, the platform controller and agent are using SCMI protocols and the transport for their communication. Now there could be different implementations available. For example, Juno board, the platform controller runs in the SCP system control processors, while the agent runs in the application processor. In a virtual world, platform controller can run in one VM, while the agent can run in another VM. So we can use SCMI to achieve the resource abstraction, and this figure shows all the drivers that are already there in upstream. Pin control will soon make it. And so we could use those all drivers to abstract all the resources in the platform controller. I may also refer platform controller as firmware going forward. So now we can use them, so we don't have to now write all these drivers locally, while the peripheral drivers can just send requests to the firmware using these drivers for the resource operations. However, there is nothing for PHY, so we cannot abstract PHY using SCMI, and there is nothing for interconnect yet. And also the PHY driver may in turn use the same drivers for its own resources, abstracting them in the firmware. This help us achieve our second goal significantly, which is that cut down on the development effort. However, the complexity of the peripheral device driver hasn't gone away. It still need to interface with so many kernel frameworks and subsystems. So can we do better? We want to turn the left side into something like much simplified peripheral driver as shown on the right side. So we are just going to use power domain and perf domain and the reset. Reset is same as here, so there is nothing interesting about it. Perf and power domain I'm going to discuss in next few slides. So our approach, we are defining logical or modeled power and performance domain. So For instance, take an example, consider a peripheral that has, let's say, two configuration. In one configuration, the clock C is running at F1 frequency, interconnect bandwidth is voting for B1, voltage regulator is set up for M1 microvolts. So let's call this configuration as level L1, while there may be another configuration like clock C is running at F2 frequency, interconnect voting B1 and voltage regulator set up on M1. So let's call this as level L2. Now we create the SCMI perf domain with these two levels L1 and L2, and driver can then request the firmware to put the device in whatever configuration it needs to be. Like L1, then it would just send the request to firmware to over the performance protocol to set the device in the level L1. Now what level L1 means, firmware already knows and will do the resource voting accordingly. So this way we can group the resources together, and we can even abstract phi as well as interconnect, and we are also cutting down number of requests that are going to the firmware as compared to if we individually use all these drivers. So continuing on that, so far in Linux, the performance domain has been associated with the compute devices like CPUs, but we are extending its usage to peripherals. So like clock scaling, dynamic interconnect voting, phi mode changes, UART baud rate changes, these are some good candidates that can be abstracted under performance domain. For example, a UART driver may define the performance levels like level 9600, level 100, 15200 and so on, and then if it needs to configure one of them, then it just sends the request to the firmware to configure level 100, 15200 for example, and then the firmware knows what it needs to do to achieve that baud rate. Could be some scaling up or down some clocks. So that all his now complexity is hidden in the firmware, and the driver doesn't need to necessarily know from one platform to another platform what clock it needs to set for the baud rate changes. Now power domain, we are grouping on and off kind of operations under power. So for example, peripheral may have clock C, so clock C enable, regulator on, power domain, this is the physical power domain on. It may also do phi init or on, and then phi resources, for example phi power domain or phi clocks on. So all those binary kind of operations we can group them under the power on operation of the SCMI power domain, and power off can just do the opposite. So this is substantially cutting on the traffic that's going to the firmware by grouping all of them. And we have like peripherals like camera with 20 plus clocks, so you can imagine that sending 20 clocks request to firmware, it just adds up. And in automotive we have very stringent requirement on the boot KPI. We have to be audio chime ready by less than 2 seconds from power on reset. So if we find opportunity to improve the boot KPI, we go for it, even if it's in tenths of millisecond. So that's one of the objective also. Okay, this slide shows the code flow in Linux. So the left side is for the perf and right side is for the power. So the peripheral device driver uses OPP framework APIs like set OPP and all those API to set the performance level, which will interface with the SCMI performance domain provider driver, which then in turn use the performance protocol layer, and then it goes over transport to firmware. The peripheral device driver for the power would use the runtime PM framework like PM runtime get and put, those API flavors. It will then interface with SCMI PM domain provider driver, which uses the power protocol and go over the transport to the firmware. Okay, those changes to that are pushed in the kernel already to make these things work. So the performance driver already part of 6.7, it's a GenPD extension. OPP framework is also extended to work with the SCMI performance domain driver. It's also part of 6.7 kernel. So now since we are using power and performance domain, and then we could have multiple of them, so we need to do attach and detach manually in the driver instead of framework doing for it. So then to simplify things for us, Wolf has pushed a helper API. It's part of 6.9 and the links are given here. Okay, this is our high level architecture. So we are using SA8775 PSOC, which is a virtualized platform running our hypervisor Gania. We have a firmware VM as shown on the left. It's a RTOS, Zephyr RTOS, multi-threaded. We have multiple vCPUs, so SMP enabled. It's the platform software. It's running SCMI server, and which is interfacing with the backend resource drivers. And on the right side, we are showing the Linux VM, which is acting as agents. Now, the thing that I want to mention here is that we are creating separate channels, SCMI channels for each device in Linux. So, for example, UF has its own shared memory, its own pair of doorbells, RX and TX. RX doorbell is nothing but IRQ and TX is HPC, and we are doing so that devices can send request in parallel to the firmware, and firmware being multi-threaded, it can process the request in parallel, and as long as there is no shared resources, they can be processed in parallel. But even if there are shared resources, then the locking in the firmware will be very fine-grained locking. Okay, this slide is on the implementation side. If we have to write the driver from scratch, there wouldn't have been any problem in the simplified version, but in Linux we actually modify the existing driver, and that's where the challenge comes, because we are not using clocks and voltage individually. Instead, we are using power and performance protocols. So the peripheral drivers now need to know which variant I'm running at. Is it the firmware managed? I'm using this term to address the same, to point to the same our approach of abstraction while the existing locally managed setup. So there could be several options available. One is like, okay, let's check in the driver for the presence or absence of the clock or any other resources like regulators and so on, but that may work for some driver, but it may not necessarily work for others, because there may be clocks may be optional, and it may not scale, and plus it's not sufficient to assume, because it's like implicitly we are assuming that if there is no clock in the DT for that node, that means we are running in firmware managed, which can be broken easily in future platforms. So it's not pretty scalable. Second option could be that we use a new device, new compatible for this, our firmware managed variant. So it's cleaner solution. It's like explicit way to decide. The driver can know explicitly whether it's running in a firmware managed variant or the locally managed. However, since the hardware IP is still the same between the two variants, we don't know if it is justified to use the new compatible. There is a difference of opinion in the community about it. Some people say because the interface from firmware to OS is changing, therefore it is justified to use a new compatible. Others have different opinion though. Then there could be an option that we use Qualcomm firmware managed, like vendor specific firmware managed DT property, like as shown here. It's again explicit and cleaner way. It's just that every node will have this repeated property, and it's a vendor specific, so it won't fly if we have to modify the third party IPs or the drivers. And also it adds up some complication. We need to modify the YAML file for the DT specification. Then we can probably drop QCOM and make it like more generic sort of vendor agnostic DT property. Again, it's cleaner and it allows us to modify the third party drivers. However, there has to be some sort of standardization, because different vendors can use abstraction differently. So we have to have some sort of common ground to be able to use it. And then one more option could be like we can use the board level platform compatible from the driver. What that means is like every driver will have to then check for the board level compatible, and every platform, whenever new platform comes, then every driver has to then include that new compatible. So it's not scalable. And also the YAML, how do we incorporate this kind of schema constraints in the YAML file? I don't know. I had started a discussion about it some 5 months back, and there was a lot of comments and concerns, and there were suggestions as well, but we didn't conclude. So I'm hoping that after this talk there will be better understanding on our work that we are doing, and hopefully we will be able to reach some consensus on this. Yeah, so current status, the firmware VM side is development is almost complete. Linux side also is under review, all the drivers. We needed to modify or extend the SMC SMC transport driver, SCMI driver that should work for our hypervisor ABI. So that's all done in 6.6 kernel, and as soon as we have some decision on the previous slide, the issue that I mentioned, the implementation, we will start sending peripheral driver changes in upstream for review. Okay, so that's all I had. Any questions? Happy to answer. Yes, sir. There is a mic here, if you can pass.
On one of the slides,
yes.
You described that SCMI can work on ACPI-based systems.
Oh.
I'm not sure that this is correct nowadays.
Okay,
I think
so
when we designed SCMI, it was an open question how to make it work with ACPI-based systems.
I think ACPI has interface that or defines interface that can work with so the agent can use ACPI, and then in turn it can use SCMI to talk to the firmware. That is possible.
Yeah, there was some discussion about translating SCMI calls to ACPI things somehow. But
Venson has comments on that.
I'm not sure that SCMI works with ACPI-based systems, like right now, Linux kernel, I mean.
I will let Venson answer that question. Yeah. Or Christian.
I think that currently works using PCC type 3 and 4. So basically the CPA system just unknowingly writes things into the mailbox, shared memory area with our SCMI packets. I've not seen firsthand, but I know that there are bit and PCC
as a transport, that's all.
Yeah, PCC type 3 and type 4 for the notification. I'm not sure that that is.
Are there any systems, real systems that has it?
I think so. I've not experienced firsthand, but that. Architecture should know that. I Shuvik follows architecture. I think there's a lot of work.
Yeah.
Around this SCPI.
Yeah, it was an open question for like last 8 years, I think.
I'm not a witness.
The second question, you described workflow on one of the slides.
Code flow? That one?
Yeah, code flow,
okay.
This one. Is it the only single workflow? I thought that SCMI nowadays supports issuing comments from user space. So requests might came not from driver, for example, from user space.
But for us, we are focusing on the peripheral drivers in the kernel for now. And for the user space also, we have our own interface driver, which exposes ioctls, and that uses SCMI. But what you are referring, I think, is the sysfs way of doing things.
Yeah,
but we are not using.
Yeah, I mean that maybe there is like more to that picture.
Yeah, of course. I mean, it can be used from user space as well.
Yeah, that's all. Thank you.
Sure.
Oh, sorry. Thanks, Nikunj. So I think the discussion which started 5 months back,
yeah,
I think we still have open-ended questions.
Yes.
From my side, I think we are happy. I'm happy with most of the approaches. I think generic approach seems to be most favorable one, but that still brings up a question. What kind of standardization do you have? For example, you set a power level or a perf level, whatever. What does that levels actually translate to? And if you are going for a generic approach, then you need to really have a definition of that each standard, so that a new vendor could actually follow those guidelines and use it. If not, you'll end up having your Qualcomm specific either compatible or you know.
Yeah, I get your point, and that would be ideal. And if we can reach some common ground among the vendors, going by that, I can just mention that even the ACPI word like P states, right? There are
Yes,
Intel
that's
P
exactly
state,
I'm trying to get.
Intel P state, AMD P state, kernel parameters.
No.
So there is like still some element of vendor specific thing, but yeah, I agree that we should try to achieve the common ground somewhere.
So when you mean performance state, I'm looking at like ACPA performance states. So if we have some kind of standardization along that lines,
Yeah.
then we could think of having a generic compatible or a generic property or whatever it is.
Yeah.
You know?
As far as I know, in ACPI example, P state has been only for CPU. I've not seen at least for the devices or the peripherals.
There's a device performance state as well.
Okay. Okay.
Maybe
But
that's something.
does it mean anything right now for the device performance state? Do we have any specification behind that on ACPI, except that it's a level a bit more performant and so on?
Yeah.
I'm not digged into more detail, but I'm looking at something on those lines so that we could really add a definition to what that performance level means. So, for example, if Qualcomm is implementing these levels, and for them level 1 means like scaling the clock to particular range or putting the device into particular state, what does it mean for NXP? What does it mean for ARM?
Yeah.
But that's for me. That's if we take the example of the UART, for example, that's linked to the device typically. This seems to be reasonable. I mean, it's not.
This is pretty general.
Yeah.
This is something pretty standard.
Yeah. So the way I see it is that you don't necessarily define a set of performance domains or levels as such. When you do the discovery phase, the platform will tell you how many performance levels it can perform on, and the platform will tell the agent what they mean. So you don't necessarily have to describe or write on a set of vendor-specific performance levels, because the platform will tell the agent what they are. There is no need for having, I don't know, Qualcomm-specific or another vendor-specific levels as such, the way I say it.
What do you mean by describing the level? Because how do we...
When you do the query, right, the platform returns the tables of performance levels, what they mean.
Yeah, but what do you mean by what they mean?
So
they just have the mapping, right?
For me, there is a name, maybe?
No, there's on the scribe levels.
Yeah.
You get the name, you got the entry, you got the level index, the indicative frequency, the power cost, and you can potentially have, you got the latency. So the platform tells you what they mean. You don't need to encode those beforehand.
Yeah, but in this case, for example, if we take the UART level 9600, the baud rate, then how do you reflect that? That's really what we want.
It doesn't necessarily have to be like...
It's a clock value, right? It's a frequency value, the way you see it.
That's it's UART baud rate, but that doesn't mean what will be the system clock of your IP, what the frequency you can have.
It could be a frequency. We could use frequency value for it, or we could just use some abstract value for it.
Yeah, you can use the indexes.
We can use indexes as well, but we are not using indexes as of now. But yes, that is an option. But we could use even abstract value 1, 2, 4, 5, whatever.
You can, yes.
Yes, and what it translates in terms of clock, that's all hidden in the firmware.
True. The way I see it is that ideally the SCMI spec is there to try to abstract too much of the hardware information to the agent, right? And then it's during the discovery that you can actually see what the platform can do.
So
that's the way I see it.
Yeah, got it.
I just want to add, it's not really specified what the levels mean. You know only that the levels are proportional to something, to the performance.
Right.
And the indexing instead are being introduced for under request of your another part of your company.
Yes.
To have something to choose, sort of a table that's not necessarily proportional in the steps.
Yeah.
I don't think that in general, besides being CPU or peripherals. There's no attempt in the spec to unify in the sense that you know at this point that your level 1 means the same for another vendor.
Yeah, exactly.
Maybe I could, maybe.
You are absolutely arbitrary now.
Yeah. So probably I might be thinking wrong. So for example, if I want, let's take an example of PCI. So when we say power domain level, whatever they want to set power domain in particular state, then what does it mean? Does it mean the PHY is initialized? Does it mean the regulators are in a performance mode? What does it exactly mean? That's the definition, because we have a common driver and it will try to set that level for everybody, for Qualcomm or for for ARM or for NXP or whoever it is. They will go and try to set that level, but what does that level actually translate to in the hardware? The definition of the level is something which is not very clear.
In this case, that's more functional level.
Yes. Yeah.
So these levels, they are separate for power and performance?
So levels are for performance. Power is just on and off.
Okay.
So according to the spec for power, the power state is platform specific parameter. So it is. Yeah, so what I would say is that the spec for the power domain protocol says the power state is platform specific parameter. So is down to the platform to do what it can, right? It's not that state 25 means do this for anyone and 26 for something. So we should
drivers should have vendor specific information embedded in there. Generic drivers I'm not talking about platform specific drivers.
So you're speaking about power domain?
Power domain. This is power domains, yes.
Performance domain. In this case,
Yeah,
it's
so
performance domain.
power
No,
right now
we
only
switched
used
to
on
power,
off.
didn't we not?
So on and off.
Both.
And
Yeah.
perf is the levels.
So, yeah, the way I see is that the spec is being put together to keep it more as generic as possible. The moment we try to encode some specific values, perhaps we lose some of these generic aspects. But I'm not saying I'm opposing this.
No.
All I'm saying is that the rationale behind the SMI spec is to make it as generic as possible. But I understand your
Yeah, I think
the spec wise,
your case.
You it's correct, and from the concerns of generic driver point, we are correct.
I think
also.
we probably
So
have
we
to
need to find some common ground to
Yeah.
see,
so whatever we can find the commonality, we can have that in the generic way, and then maybe hybrid approach where some part is still vendor specific, some part is
can
common.
I add something?
But yes.
I just wanted to add something to the discussion. The abstract scale for the performance to SCMI came from ACPI spec, so some answers might be there. And for CPUs, we used CPPC from ACPI. It describes abstract scale, so some answers might be there. Well, in definitions.
Yeah, for CPU, yes. For devices, that may not be applicable as is. But yeah.
The DPS defines all the supported device performance states in the ACPI. So it's something I'm reading right now.
So I mean, the spec might say something about this ACPI spec, but I mean, there's no support for this in the kernel. So that's probably reasons for that. I guess.
Yeah, I get your point. I think, you have a valid point. We need to have some sort of common generic
I
ground.
think when we the problem is mostly when we're touching the generic drivers.
Yeah.
And we are introducing something pretty new.
Yeah,
And we don't want to be in a state, end up in a state where we can't scale.
yeah.
That's
Yeah. I think, we need to continue pursue some more discussion on this, while I think we need some closure, at least interim closure on this, so we can start our development and push the patches, because there was an ask on the thread that when can we see some patches, because that enhance some more
It does,
understanding of the thing that we are doing. So as I talked to some of the maintainers yesterday, including Vincent and Ulf and even Bjorn and Arndt. They were suggesting a new compatible. So, and I also, I think, convince you up to a certain degree to drop your reservation.
There are two problems to it. One is identifying that your system is is supporting that perf on devices. That's one problem. The second problem is how do we generalize the interface itself, the specifications of what the performance level are, power means. So there's a device limit. You could ask.
I guess you can just start using the clock rate. As if it's there, I would use that, and maybe that's a start for finding some common ground.
Yeah, you could start at some levels.
But that would also be not common to every driver.
Maybe not, but in cases where it is, that's maybe something to start with. But generalizing on levels.
Generalizing levels would take some good amount of time.
We need to provision that thing. That's something. I know we can't
in the long term,
everything, but we need to have that provision to in future to expand to that situation. But on going back to compatible, probably Christoph is here. You could get an opinion on how this should be done.
I think. So I think we are running on time. So. Well, thank you very much for all the questions. Thank you.